recorded right now.
Is 181 gigabytes enough to record almost an hour?
Well,
welcome everybody. Give it a few more minutes for everybody to get joined in and situated. Looks like we have a handful joined in already. We'll give a few more minutes for the rest of everybody to join before we kick things off. So it is the top of the hour, and with respect to everyone's time, let's go ahead and get started. First off, my name is Dan Richter, Associate Director of Relationship Management here at Commonwealth Associates. I want to welcome all of you today and thank you for joining us to learn more about campus utility distribution with a focus on combined heat and power, which also goes by other names like CHP or cogeneration. Each quarter, we'll be providing you with a way to expand industry awareness on timely topics or issues currently pertinent to the industry. We are providing these learning opportunities and information as an extra value add for our clients, partners, and friends. So please keep an eye out for notices of upcoming events. At the conclusion of our presentation, you will receive a certificate for each webinar you attend, as well as details regarding your PDH. Today, I have asked my friend and colleague, Mike Hitchingham, to share his extensive cogen experience and insight on an interesting case study for all our benefits. The chat feature within GoToMeetings will be open for the duration of the presentation for you to jot down any questions as they arise, and they will be addressed at the end. We will also be running several quick polls throughout the discussion and look forward to your feedback on those items. Now, I'll turn it over to Mike to introduce himself.
Thanks, Dan. Good day, everybody, and thank you for joining us today for a subject I have been blessed to be involved in for over 2 decades. I am far from an expert, since as I'm sure many of you are aware that as soon as we master something, the industry changes on us and all we can do is adjust. From my experience with a few companies and many clients, I want to share some general information on combined heat and power and the options available for you to consider. I've worked on projects that range from small town factories that only needed 10 kilowatts of power and a little hot water for showers, to large municipal steam supplies with plants providing hundreds of megawatts of power and millions of pounds of steam per hour. To make sure I have not put you to sleep, there will be periodic polls where there may or may not be a right answer, and that will lead us to our first poll, so I'll turn it back over to Dan.
Thanks, Mike. When we're talking power, we know it ultimately begins and ends with a strong defense. So to make sure everyone is familiar with these polls, please select your answer to this example question in the chat bar on the side of your screen. So this is just an informal poll to make sure everybody understands how they work throughout the presentation. If you have an issue voting, please raise your hand or ask it in chat, and our support team will respond to you. So which college football team has the best defense coming into the 2021-2022 season? Hey, tie between Alabama and OSU. Looks like we have some Midwest folks on the call, so good to know. We'll give it back over to you, Mike.
All right, well, personally, I didn't see Ohio State on there. I see Ohio, but I'm sure the Bobcats will have a very good defense. All right, just confirm for me, Dan, that you can see the screen again?
Yes.
Excellent, thank you. So I will consider today a success if you walk away with a decent sense of the following: options and applications for combined heat and power, differences between steam and hot water distribution, fluid distribution methods, and a way to gauge the benefit you stand to receive from your combined heat and power project partners. So let's get right into it. So combined heat and power options. First, let's get some of the definitions out of the way. Combined heat and power, also known as cogeneration, is the concurrent production of electricity or mechanical power and useful thermal energy, heating and or cooling from a single source of energy. It is a type of distributed generation which, unlike a central generating plant, is located at or near the point of consumption. It can be a suite of technologies that can be used with a variety of fuels to generate electricity or power at the point of use, allowing the heat that would normally be lost in the power generation process to be recovered to provide needed heating and or cooling. So in a quote unquote traditional setup, facilities typically get their electricity from the grid, which is generated at a power plant that could be hundreds of miles away. And then they would generate heating and cooling on site using a boiler and a chiller. This instills an efficiency into the system because there is fuel needed at the power plant to generate the electricity, and then additional fuel used on site for creating the heating and cooling. And in typical plants, you can get around 50% efficiency for these. Obviously there's give or take on that. But by utilizing the waste heat from the electrical generation, you can also create the heating and cooling you need on site in a combined system. And by using the waste heat, you can increase your efficiencies up towards 75%, give or take. Now, the customer can still be connected to the grid to provide additional electricity beyond that that may be provided by the cogeneration or as a backup during outages. There are two common configurations. One would use the fuel as the prime mover. So you would have fuel coming into the site that would go to an engine or a turbine. You would burn the fuel within there. Those would be connected to a generator, which would create the electricity that can then be used on site for the buildings, or could also be exported off to the grid. Now, the engine or the turbine has the waste heat, and you can use a heat recovery unit to generate either steam or hot water. And then that steam and hot water can be used for cooling and heating of your buildings and facility. In addition, if you have excess steam pressure, you can also add in a steam turbine on the heat recovery side to generate additional electricity. On the second configuration, you would actually use the fuel into the boiler, where you would first create the steam, and the steam would then go to a steam turbine, which creates the generates the electricity, which goes off to your buildings or to the grid again. And then from the outlet of the steam turbine, you can again have steam or hot water, which can be used in cooling and heating. So it really just comes down to where you're going to put the fuel into the system. Now, for combined heat and power, there are 5 technologies that account for approximately 97% of all plants. They consist of reciprocating engines, gas turbines, microturbines, fuel cells, and boilers with steam turbines. There are advantages to each type, so you would need to determine what your design criteria are, what's most important to you, and determine which technology would be best. This chart does a good job of summarizing the difference between technologies on a broad range of items and was adapted from the U.S. Department of Energy Combined Heat and Power Technology Fact Sheet Series 2016. So if you have any issues with the numbers, don't blame me, I'm just the piping guy. And while I won't go through and read the table line for line, let you all take a look at it while it's up on screen, I will point out a few of the notes from it. So all performance and cost characteristics are typical values and are not intended to represent a specific product. Total installed costs will vary depending upon the site-specific conditions and regional variations. The total installed costs shown for the steam turbines are for a steam turbine only, so please keep that in mind. Does not include the cost for a boiler, fuel handling equipment, steam loop, and controls. They took the assumption that the facility already had those items in place. Fuel pressure was adapted from the catalog of CHP technologies from the EPA, Combined Heat and Power Partnership 2015. So as you can see, different technologies will grade out better depending upon the size of the unit you need, the fuel you have on site, the pressure of the fuel you have available, and how you plan to use the plant in the long run. And with that, I'm going to turn it back over to Dan for another poll.
Yeah, so here's our first real poll pertaining to the presentation. How would you describe your familiarity with the US EPA CHP partnership? Please select your answer to this question in the chat bar on the right side of your screen. Remember, familiar with it, heard of it, haven't heard of it, who cares?
I hope they care a little bit if they're on this.
So it looks like the majority actually haven't heard of it before. So that's interesting, and hopefully an avenue to gain a little insight through this presentation and get some good questions going through the rest of the presentation. So with that, I'll hand it back over to you, Mike.
Thank you. So next we'll go into, once you've generated your electricity and you have output of either steam or hot water, how do you decide which one you may want? And there are benefits to both. And it's something that you'll have to evaluate what is the most important for you. Steam provides more energy per pound. As it indicates, 11,050 BTUs per pound for steam versus 180 for water. You have lower pumping energy needs. There's no steam pumps. You're just using the pressure of the steam to get it from the boiler to the end user. You have smaller condensate return pumps to get them back. With steam, you can also have additional uses beyond heating. Sterilization, humidification, food processing. I have quite a few customers, particularly in cities, that are sending steam to hospitals, in particular for the sterilization processes. Steam also gives you some pipe savings due to the size. While the steam supply size is similar to that of a hot water supply, the condensate return is significantly smaller than a hot water return. Now, on the hot water side, the technology is far more common knowledge to operators and maintenance staff. I think we all, not all, but a lot of us have hot water systems in our own homes. We have furnaces, little hot water boilers, different things like that, and understand a little bit of that knowledge already. They have lower O&M costs, increased efficiency, tend to have lower idling and cycling losses, require less makeup water. Anyone that's worked with a steam system knows there's just leaks, whether it's at drip legs where you have condensate falling out of the system and you're losing that water, to just a leak at a flange or something. You tend to be losing a certain amount of steam regularly. They also have lower chemical treatment costs and provide for higher safety. So when there's a hot water leak in a pipe, you tend to just have water, that drips out or pours down onto the ground. Whereas if you have a steam leak, if it's in a confined type of area, then it can actually fill that area up and be a hazard in that way. But you've also likely heard of the stories of plant personnel who walked along with a broom in front of them, swinging it in case there was a steam leak, and then having it cut the broom in half just because there's so much energy to it. So once you've decided steam or hot water, there are a few different ways you can get that steam or hot water from the plant to where you need it. And routing pipe through a building in smaller facilities is one thing, but what about when you're trying to supply multiple buildings on a campus, in an industrial complex, or in a city? Similar to the prime mover technologies, there are multiple ways to do it, and what you choose will once again depend on your design priorities. As you can see here, we have a few different variations. In the upper left, you have multiple lines routed above grade on a pipe trestle. And in the middle, you have a direct buried system being installed in an open trench that will be covered after installation is complete. In the upper right is a precast round tunnel. The lower left is a cast in place concrete tunnel, and the bottom right is a pipe trench that is currently under construction and will also be buried once complete. Let's take a brief look at each of these methods. So each type of installation will have its pros and cons. For above grade piping, the ease of construction by not having to open up the earth beyond potential piers leads to a lower cost installation. In addition, since it is above grade, anybody walking near them will notice if there's something out of the ordinary beyond what would typically be looked at during a scheduled maintenance walkdown. And when maintenance is performed, you would not have the added cost of having to open the earth back up again. But on the downside, you must have the real estate to run the pipe above grade. And while on an industrial complex, having above grade piping may not be a big deal, I can tell you it's frowned upon on college campuses and in some business parks because for some reason, some people think piping is unsightly. And finally, you also need to worry about the security, not just from those that would intentionally do harm, but also from curious bystanders who might accidentally lean up against the pipe or a pipe support and accidentally burn themselves. As you can see on this support, even with it insulated, heat can travel through here, so there is the potential that this could be hotter than people would expect. With direct buried pipe, you minimize the visual impact since the piping is now below grade and the buried depth is typically minimized to about the frost depth. Of the buried options, this is by far the cheapest, as all you have to do is open up a trench, install the pipe, and then restore the surface. However, since you have no access to the pipe, it can be very difficult to locate and repair leaks, and installing direct buried lines in areas with existing utilities can be challenging, particularly for steam piping where you need to avoid low points where condensate can collect. In addition, handling the pipe expansion will either require buried expansion loops, which takes up more real estate, or expansion joints that need to be placed in manholes or vaults to allow for future maintenance. Now, another option for buried piping is a pipe in a trench, and this removes the soil contact with the pipe, which can also be an issue when direct buried lines are improperly installed. And since they tend to be near grade, they require similar excavation as a direct buried pipe, which narrows the width needed for your excavation. Once you put the top on the trench, accessing the pipe requires a removable top or for a cast in place top to be demolished. One is additional cost upfront, while demoing is a cost anytime you need to access the pipe. So if you put a removable top on, it's going to cost a little more upfront. If you choose to cast it in place, anytime you have to go in to do a repair, you have to break apart that top and then reform it and repair it. And finally, if repairs are needed, even with a removable top, there are space constraints. As you can see from this design, you can get the top off, but even then, while we did have a small aisleway here in the middle to allow walking down the trench, if you're having to do any welding on the outside pipes or changing insulation or repairing supports, you're going to have to be climbing over pipe and getting in awkward positions. We all know the welders can handle this, but they'll grumble at us engineers while they have to do it. The last option for getting your pipe underground is locating it in a tunnel because it gets it out of the site and still allows for easier inspection because you can just walk right through the tunnel. And since you can walk through the tunnel, periodic inspections can be performed to allow for preventative maintenance rather than reactive maintenance. And unfortunately, reactive maintenance is what typically happens with direct buried and trenched pipe. You don't do any repairs until you know there's a problem, whereas with tunnels, you can go in based on the age of things and you can repair them leading up to a potential issue. Tunnels can also make future expansion easier because it allows for doing additional takeoffs anywhere along the line. And also, if you eventually need additional capacity, then routing an additional line within a tunnel can be done relatively easily, as long as you've allowed for space for that for future additions. Cost is by far the biggest detractor to building new tunnels. You have deeper excavations, you have support structures that you need, there are access requirements and ventilation, just to name a few key areas that really add up the costs. And with walk-through tunnels being 7 to 10 feet in height typically, finding the open space to build them can also be difficult unless you're on a greenfield, nice clean campus. Another consideration is depending upon the number and location of access points. Some tunnels are classified as confined spaces, which will add costs for all future work within that tunnel. So where do you start to try to find the best option for you? Depending upon your needs, you'll want to do an overall system evaluation that will include looking at your system demands, which will lead to an equipment sizing. You'll then want to develop preliminary plant layouts to determine the optimum location for the plant, which may include evaluating various right-of-ways and land acquisition. Part of locating the site is also determining how the steam and/or water will be distributed and options for routing the pipe. With a preliminary design in hand, you can develop an economic evaluation to look at the capital costs, the fuel costs, and the operating and maintenance costs. And these are all things we at Commonwealth would be happy to help you out with, and we have lots of experience with that. So before I go into the case study, I'm going to take just a quick drink. Apologize. As I mentioned earlier, every time we think we have things figured out in this industry, things change. So we just kind of have to roll with it. It is a broad range of experience that can be of benefit to our clients, but let me discuss an example where things didn't go quite as well. Out of respect for all parties, I'm going to keep the names confidential. The client operates a cogeneration plant that supplies electricity to the grid and steam for a variety of uses to multiple local customers, one of which was a large manufacturer that had its own dedicated steam line from the plant. The engineer record was a small engineering firm that had about 5 previous district heating projects on their experience list. In February of 2015, the cogeneration plant supplying the steam to the local manufacturing plant through a combination of above grade and buried piping tripped. Due to the plant trip, the client sent their staff out and inspected the entire length of piping and discovered that a portion had separated from the support pedestals and came to the rest on the ground, which is just a big fancy way of saying it fell off. As you can see there, it's resting on the ground. Client brought the firm I was working for in to perform an independent engineering review. First and foremost, they wanted to know, could they continue to operate in the current condition? That's right, at no point had they brought the system down after discovering the problem. Partially out of concern for shutting down, it could make things worse, and partially because of their contract to the manufacturer that required steam be supplied 24/7. And while they had an alternate source, it was not reliable and they anticipated it would have outages. In addition, of course, they wanted to understand what caused the problem so they could avoid it in the future. And they wanted an opinion on the adequacy of the existing design and an opinion on repairs needed to bring the system back to a normal operating state. So first and foremost, can they continue to operate? We were on site within a day to inspect and walk the entire system down in negative 30-degree wind chill. And even for a northern boy like me, that was cold. We then developed an independent piping analysis to model the pipe falling off of the supports, as well as a model for the pipe as it rested on the ground to determine the predicted stress levels. We then evaluated since it was a steam line, we evaluated the fact that we now had a new low point. As you can see from this picture, the support pedestals were quite tall. I believe these were over 6 feet tall. So when the pipe came down and rested on the ground, all of a sudden we had a new low point in the system where condensate could collect. In the end, we recommended that they could continue to operate as long as they put a new drip leg in. And that was hot tapped into place right around here. And they had no issues operating in this condition from the time of the initial observation in February to June when the repairs were fully implemented. So the piping model, with a few screenshots here, indicated only 2 areas of concern in the section during the event when the pipe actually fell off. And both of those were at the anchors, which are circled at both ends. And this was due to the pipe bending. And while the values were above the ASME code allowables, they were well under the ultimate yield values, indicating imminent failure was not a concern. The sections of pipe were recommended for replacement for long-term system reliability, but they did not need to bring the system down immediately to do that. They could perform that with any other repairs later. It was determined that in the now operating condition, the pipe can continue to operate short-term to allow for a proper evaluation and design period. So now that we had them continuing to operate, the question turned to why did it fall off the supports? We looked at multiple things. The three biggest ones in the end were evaluating water hammer, which was the engineer of record's claim that the plant trip created a water hammer which forced the pipe off of the supports. We also looked at unrestrained wind loads, and then we also looked at unrestrained thermal movement. So first, the claim for the water hammer due to the plant trip. We took a thorough review of the plant's operating conditions before, during, and after the trip, and found that the steam pressure did drop from 240 psig down to 110 over an approximate 10-minute period. Pressure was maintained at 110 for about 1 hour and then dropped down to 30 psig over approximate 7-minute period. There were no sudden spikes or wave type fluctuations observed. There were minimal temperature variations, and in the end, superheated steam was now leaving the plant when they would typically be sending saturated steam. The pressure transients occurring over a period of several minutes were not believed to be sufficient to have caused any significant dynamic condition within the piping system. It was the opinion that lowering of the line pressure in the manner indicated would not have resulted in significant generation of condensate within the pipe. Rather, any condensate present, such as in drip legs, would have flashed to steam. In addition, there were approximately 2 miles of pipe with numerous elbows, supports between the plant and the actual failure location, and there were no other failures anywhere else in the system. And those that know water hammer know that depending on where this hammer begins, your largest force is near the generating point of that water hammer, and as it goes down the line, it will decrease. Now, for high wind concerns, this one came about because a review of the engineer record stress model indicated that at some point during their design, the occasional wind load was actually removed from the file, which raised some red flags. The inspection of the actual area found that it was protected by a berm and a tree line from the direction the wind would have been coming from during the period where they believe the pipe had fallen off. And the maximum wind speeds for that month were not out of the ordinary. As you can see here, we have a maximum wind speed of 15 miles per hour. We do not get hurricane strength winds in this location, but we do get significantly higher than that. The confirmation pipe stress model also indicated that the maximum wind speed observed would not have forced the pipe off of the supports. In fact, it would not have moved it hardly at all. So finally, we took a look at the unrestrained thermal movement. A review of the operation for the previous year indicated that there was a history of support issues. There had been multiple support modifications to extend base plates due to movement observed outside of document design conditions. Slide plates had delaminated and broken, which resulted in friction above design. You can see one of the slide plates right here just resting on the concrete. And poor quality control during construction resulted in offset posts, leading to loads imparted improperly on base plates. So as you can see here, the post within the concrete was designed to be in the center. It was offset some. So obviously during construction, they had a little bit of issue there. And then the section where the failure occurred was approximately 500 feet between anchors. And we're looking at this section right here. So we had an anchor on this end with an expansion loop in the middle. There were no guides located between the anchors. The only guides in the entire above grade system were single guides leading in and out of the ball joints for vertical loops. So again, the next section had an expansion loop, 400 feet, no guides. The next loop had 200 feet, no guides. Over here, we did have guides. There were ball joints. These jumped up and over a road, so they had ball joints here, and they did have guides coming in and out of those. And just for information, while the 400-foot section did not fall off, it was also closer to the edge than it should have been. So as mentioned, multiple supports between the anchors had plate extensions added by the engineer record after startup to account for excess movement. Maybe a little difficult to see in this picture, but right here, there's a weld. So this section of plate over is all new. In addition, they started adding loads to the plate such that they had to add stiffeners in, such that the plate wouldn't bend. And this was noticed on multiple. And it's really hard to see, but also the slide plate was extended. But even with all of that, this pipe had moved past even the extension. So typically, expansion loops are installed with two guides in and out of the loop to control growth into the loop and force the elbows to bend and take up the pipe stress. Without the guides, the pipe will take the path of least resistance, which is typically bending the entire length. So on this system where they have guides coming in and out of it, the pipe would move along this axis and bend at this elbow all the way around. But without those guides, all the pipe's going to want to do is bend the entire length and move laterally. And the longer the run, the more lateral movement you're going to see. And this is somewhat evident in the fact that the 500-foot length did fall off while the 400-foot length was only near the edge. So there was no conclusive evidence that a single dynamic or transient event was the root cause. There was also no evidence found to suggest that the temperature excursions went above the 450-degree design temperature for the system. And it was the opinion of the team that unrestrained incremental lateral movement accumulated to result in the total lateral movements observed, including those sufficient to leave the segment with this expansion loop unsupported. So once we came to the outcome, basically we decided you need to add guides. So how were they going to add guides to these existing supports? This was a very fast-paced project, so we didn't take the time to come up with multiple CAD options. We just hand sketched them out. We came up with 3 different options for them. Option 1 was simply adding bar steel or angle steel to either side of the slide to prevent the pipe from moving laterally. We'd add kickers as needed, would likely require additional piers. The issue we have with this system is the fact that the existing pipe support shoes were clamped onto the outside of the pipe insulation. So this was a pre-insulated system, so you had your steel pipe, you had insulation, and then it had a, I believe it was HDPE exterior, and then the supports were clamped onto the outside of that. So any lateral force was likely going to result in the pipe just continuing while the support rotated. Option 2 would also allow them to continue to use the existing clamp-on supports, but would build a frame around the entire pipe, and we would actually use the clamps to help guide the system. And we did work with the manufacturer for these clamps to verify that they could handle the loads on that portion of the clamp. We, in addition, would add bar steel or angle steel at the bottom to take up the initial force, such that the force up here was a little bit less. And we also would have added plates up top to just, ensure that the pipe wouldn't lift off this entire thing. Third option was kind of a variation on the first one, where to prevent liftoff, we would use angle or bar steel that would come up and over the base plate. And then the clamp would be replaced with a weld-on shoe support. And the reason to get rid of the clamp, again, even with this support, if you're putting the lateral force down here, the whole thing is going to want to rotate over and you would likely bind up the whole support. So while the middle option was the highest cost, in working with the client, the contractor, the fact that they wanted to keep the system operating as much as possible during construction, they did choose option 2. And we continued with designs for that one. So from that, then we created a base sketch that was developed into 6 different standard supports. And this allowed us to accommodate the variety of site support conditions. Each support allowed for fabrication of the most parts in the shop with adjustment made in the field to final dimensions. This support was for a concrete base with a tall steel post. The initial support was only here, so then we built the frame around that they would attach. And for those with high lateral forces, additional kickers were included that would push the force back down into the base. And this dimension could vary from support to support because none of the supports were the same on this site. So each one was 6 to 9 inches different, and it just kept moving up and down. We also took the same basic concept, and they had supports that were resting directly on top of the concrete piers. So we developed this support that would bolt into the concrete and could be attached while the system was in operation. And then the last one I'll show you was one that was just for shorter steel posts. This one did not have any kickers back down to the concrete because the loads were lower. And I guess I would like to clarify that I've said they'd install it while it was operating. They did have to go to a shutdown to get the pipe back to the center position. They also obviously needed a shutdown to replace those 2 sections of pipe. So while it was cold, they did any final attachments, for gap dimensions and whatnot, so that when it started back up, the whole thing didn't start up in a skewed position. Now, those support designs were then implemented into their plan drawings, where we called out where they needed new guides and what type. And it's very difficult to see this, but we're calling it type 6, type 4, more type 4s, and that way they knew which support they should go take a look at and install. And right here's the loop. So we added 2 guides in and 2 guides out. In addition, where there were longer runs, we also added supports in the intermediate spaces to ensure proper travel of the pipe. So in the end, the system has observed no additional issues since the new supports were commissioned. Client is still a valued customer, and thanks to strong communication between the client, the contractor, and ourselves, we were able to deliver an improved solution on time and with minimal impact to the end customer. And my hope from all of this is that the engineer record took the lessons learned from this project and implemented them into any future work. And with that, I'm going to hand it back over to Dan for one last poll, and I thank you for your time.
Yeah, thank you, Mike. Appreciate the quick overview of CHP as well as an interesting case study and overview of that case study. So to help us schedule future topics that are most valuable to each of you, please select the answer to this question in the chat bar on the side of your screen. What future webinar topic would be of greatest interest to you? Grounding, microgrids, NERC compliance, protection schemes, or renewable integration? Wait and see the results. Let's see. Renewable integration. Okay. Interesting. That's good feedback, and appreciate the insight into future content ideas, and appreciate the feedback. We'll open up the floor for questions and comments. So either raise your hand if you'd like to speak, or type the questions into the chat or question bar. And again, I'd like to thank everybody for taking the time to join Mike and myself today for what I consider a very interesting topic.
They're going to let me off easy.
Might. Not seeing any hands raised yet. Nothing in the chat window. So Mike and I will hang around for a few minutes if anybody's typing in some questions. Let's see. Here we go. We got a few questions. All right. So one question, Mike, any studies, reports for using CHP to meet greenhouse gas reduction goals?
Yes, we have done studies on various methods that you can use to reach any green energy goals you may have. CHPs are a great way to do that. If we can come up with the payback and determine all that, but in general, if you're going to need to use electricity anyways, by being able to combine that with a CHP plant and use the waste heat for steam or whatever you may need it for, it does help you meet those energy goals. And those are studies. We have a group that performs all of that. They do, all the front legwork for you to come up with a study that tells you the benefits. And they don't always work. We'd like them to always work, but we will give the true answer on the payback. Obviously, if it's a 40-year payback, it's not worth it. If it's a 3-year payback, it's a great thing. Yep.
I mean, coupled with the efficiency gains too, right, Mike?
Yep, absolutely. Yep.
Okay, next question from Ron. Was the original engineer and design company responsible for the repair costs?
There was litigation. There was a settlement. I don't know that anyone came out of the settlement perfectly happy. So yes, they did contribute to it. They did not pay for the full amount though.
Okay. A good question from Ryan. Were there any challenges to getting the existing pipe back on the supports?
Oh, that's a great question. I don't know. It was a challenge. It was a fun challenge. So the contractor that actually, and it was the contractor that installed the pipe originally, and this is a good lesson for everyone as well. They came in and they were very open that there were some construction issues, with the offset posts and whatnot. Since they were open about it, they were welcomed back. They actually brought in, I believe it was either 4 or 5 cranes, and they lifted the entire section, the 500-foot section that was on the ground. So they cut the ends, they replaced that pipe, and then they lifted that entire 500-foot section at one time. I happened to be on site when they did that. It was amazing to see. Just all the crane operators working together, and they just inched it up into place. And we had a lot of prep leading into it. We actually did some piping modeling for what was going to happen, because obviously now you're lifting 500 feet of pipe from 5 locations rather than having supports every 20 feet or so. So what was going to happen to the pipe when you did that? And so there was a lot of prep going into it, but the actual implementation of it went far smoother than I think any of us could have expected.
So Mike, I'll ask a follow-up question to that. Do you remember how long the end user, the ultimate client, was offline for?
So fuzzy memory, but I would say they actually probably had 2 or 3 shorter outages. It wasn't one long one. The for replacing and lifting the pipe. I want to say that was done over a long weekend. Again, the contractor brought in enough welders that they did both ends at the same time and did that over a long weekend. They then put it back into service so that the manufacturer didn't lose a lot of time. Then they put all the supports in. And then I believe, I can't remember if it was one or two more short outages, but again, they would have been over weekends where they would bring it back into the cold position, do the final installations, and then they would heat it back up. And
So
from
the
recollection, I
goal.
want to say they only did one more. So really, I'd say they lost maybe 6 days, 7 days of production, might have been less. They actually did bring in rental boilers to make up for that because the facility didn't go down for those periods. It truly was a 24/7 operation.
So the ultimate goal from evaluation through solutions was to keep that end client operating the whole time safely and efficiently.
Yep, safely and efficiently. The LDs that would have resulted from them not getting steam for an extended period far outweighed the cost to rent boilers or to do any of these other things. Yep.
Okay. Any other questions before we conclude our presentation? So I'll ask one final question to wrap up, Mike. When you're looking at a typical facility that utilizes CHP, can you give a quick high level, what type of facilities?
Man, you could have prepped me for that question, I think. No, type of facility, it can vary greatly. A lot of college campuses do use CHPs, especially up here in the north because they have large heating loads. But even in the southwest, in the south, where there's large cooling loads, they'll use it on chillers. So hospitals, as I mentioned, they like steam for sanitizing. So hospitals will do it, college campuses. But as I mentioned, small businesses, there's a great benefit to it. For most manufacturing type plants, if you have the space to, and for the small ones, these are small units. We just looked at one recently that would have fit in my basement basically, with 3 units, and it would have given them redundancy. So industrial definitely can use it. We've recently worked on one that was for a single customer, but they had 3 buildings in a downtown setting. So they put the plant near one of them, and then they routed pipe to the other 2, which allowed them, to become a little more autonomous. So really, it can benefit lots of people. I'd say those are the bigger ones, though.
Okay, thank you. One of the last questions comes from Joseph. Are you aware of CHP being used in automotive paint shops?
Yes. I don't have as much experience with those. Automotive definitely have their plants. They're huge, and the end user on this one was an automotive in actuality. But because automotive plants, they take a lot of electricity, but they also need a lot of steam and hot water plus compressed air. They typically will, at their larger facilities, build a central plant that houses, the heating, the compressed air, water type things. So yes, though it is a big area that could be looked at.
Thanks, Mike. So that looks like that wraps up our questions, unless anybody has a final one to put in. Other than that, we'll wrap up our presentation. If you have any follow-up questions, feel free to reach out. There should be a contact us from the original invite, and be on the lookout for a follow-up communication from our team. So thank you again for your attention and participating in this webinar, and we look forward to bringing you future topics and information.
Thank you, everybody.